Welcome to your channel, Silent Mind Studio, and thank you for listening to us. You've joined us for The Deep Dive, where we take on complex topics, pull back the layers, and really get straight to what you need to know. Today we're plunging into a fascinating area, something that, feels like it belongs in science fiction but is rapidly becoming, well, a reality. It's the quest to teach AI to understand human emotions. It's a topic that has truly intrigued us, filled with, frankly, surprising facts and some pretty profound questions. You've given us a stack of sources, articles, research papers, notes, and our mission today is to navigate this landscape together, extracting the most important insights and understanding what's really going on in this push for emotionally intelligent machines. Have you ever looked at a machine, maybe like the camera lens on your computer or phone, and wondered if it could truly see you? Not just, identify your face, but understand that subtle shift in your expression or the tone in your voice that speaks volumes beyond your actual words. It's an ancient dream, really giving life and understanding to the inanimate. And this deep dive is the story of humanity's audacious quest to teach machines about emotion. It's a journey, as you'll hear, full of surprising sparks, some missteps and questions that get right to the heart of what it means to feel and what it might mean for a machine to even try and recognize that.
And that journey, as our sources really show, it's not a new one. It didn't just begin with modern AI, not at all. Even back in the mid-1960s, when computers were these room-sized giants capable mainly of calculation, a peculiar question emerged. Could they converse in a way that felt, well, human?
Right. This is where Joseph Weissenbaum at MIT enters the story. He created this program called ELIZA. And by today's standards, it was astonishingly simple. It didn't understand language in any real sense. It cleverly mimicked a therapist using a technique called pattern matching and substitution. So if you type something like, "I am feeling sad today," ELIZA might recognize that I'm feeling X pattern and respond by flipping it back as a question. Why do you say that you are feeling sad today? Just reflecting it.
And Weissenbaum's original intention, interestingly, was actually to demonstrate the superficiality of communication between humans and machines. He really thought it would show how easily people could be tricked by simple tricks. But the unexpected happened. People genuinely confided in ELIZA.
Really?
Oh, yes. Secretaries, colleagues, even, experienced academics found themselves pouring out their problems, their feelings, projecting understanding, empathy, even wisdom onto this very basic program that was essentially just, reflecting their own words back to them.
That's the famous ELIZA effect, isn't it? That tendency we have.
That's exactly it.
And Weissenbaum was reportedly quite taken aback, even dismayed by it.
He was.
It revealed something profound about us, didn't it? Our deep human tendency to seek connection and project understanding and meaning, even onto something as rudimentary as a text program. It highlighted that blurry line between a machine simulating understanding and any kind of genuine comprehension, and how our own desire to find connection can fill in the gaps.
That ambiguity in the machine's response, it turned out, could act as this powerful mirror, making people feel heard even if the machine itself had absolutely no internal state or comprehension whatsoever.
So ELIZA was this early hint of the complexity, simulation versus real understanding.
Exactly. And as decades passed and technology advanced, that ambition grew. The thinking went. If a simple text program could evoke such a strong projection of understanding, what about a machine that could interact with us through sight and sound, with something resembling a face?
Which brings us, I guess, to Kismet. This is a research project led by Dr. Cynthia Breazeal at MIT, late 1990s.
That's right, late 90s.
And Kismet wasn't just software. It was a physical robotic head designed specifically for social interaction with humans. It had these large expressive eyes, eyebrows, and a mouth deliberately designed to be somewhat alien, apparently, but capable of a range of movements. Its goal was to perceive social cues from people using cameras as eyes, microphones as ears, trying to pick up on visual and auditory signals like facial expressions and tone of voice.
And Kismet was built to respond in kind. It would coo, babble, shift its gaze, and move its various facial features, its eyelids, eyebrows, ears, mouth, to mimic these programmed expressions. Expressions intended to convey states like interest or surprise, happiness, maybe frustration. It was a highly visible, tangible step towards building machines that could engage socially and attempt to interpret and respond to human affective cues in real-time interaction.
But, just like with ELIZA decades before, interacting with Kismet raised that same fundamental question again, didn't it? Was it genuine understanding on Kismet's part? Or was it still largely our human tendency, the ELIZA effect, but now in physical form, projecting emotional intent and understanding onto the machine's designed responses.
That's the core question that kept coming up.
Still, Kismet was clearly a pioneer. It was this bold exploration of how a machine could look, listen, and respond in ways that felt social, pushing the boundaries of machine interpretation of things like a smile or a subtle change in vocal pitch.
And these early intriguing efforts, ELIZA showing our projection, Kismet exploring physical-social interaction, they eventually coalesced into a formal scientific field. This is where affective computing enters the picture. Coined by Rosalind Picard, it's defined as computing that relates to, arises from, or deliberately influences emotions.
Okay, let's unpack this a bit. Why is this even a necessary field? What makes teaching computers about emotions such a big deal?
Well, our sources highlight the fundamental reason. Emotions are not some, optional add-on to the human experience. They are absolutely central to who we are. They profoundly shape our intelligence, how we communicate, how we make decisions, and how we interact socially. They are deeply, deeply interwoven with cognition, influencing everything from perception and learning to memory and creativity.
Right.
Traditional computers are built on logic, pure logic. For AI to truly interact intelligently, naturally, and effectively with humans, it needs to engage with this fundamental, often non-logical aspect of our nature.
So it's really about moving beyond just making computers functional or usable to making them more effective or emotionally aware in their interactions.
Precisely. There's a powerful vision driving this field, though it's, as our sources point out, quite dual-natured. On one side, there's this deep human aspiration for more natural, perhaps even empathetic connections with our technology. Think about AI applications aimed at augmenting human well-being.
Oh.
AI potentially assisting in mental health support, providing personalized education, or acting as a compassionate virtual companion.
Mm-hmm.
These roles traditionally require empathy and an understanding of emotional states, and there's a real drive to build AI capable of this, interacting on a more, human-like level.
Like an AI therapist that could maybe detect when you're distressed, or a tutor that adjusts its approach because it senses you're getting frustrated.
Exactly, that kind of thing. But, and this is where the tension really lies, there's also a very strong drive from utilitarian and commercial objectives. Affective computing is being rapidly explored and deployed in areas like marketing, to gauge consumer reactions to products or advertisements, in human resources to potentially assess job candidates during interviews, or in customer service to identify agitated callers and perhaps respond differently.
So that duality you mentioned earlier, the aspiration for genuinely helpful, maybe even empathetic AI versus the pursuit of, utility and commercial gain. That tension seems like it really permeates the field, doesn't it?
It absolutely does, and it's a critical aspect to keep in mind as we explore this technology throughout our discussion today. And this duality points directly to both the significant promise and the substantial peril of affective AI. The promise is vast. Truly natural human-computer interaction that feels less like talking to a machine. Revolutionary potential in healthcare, perhaps enabling earlier detection of conditions like depression or dementia based on vocal or facial cues. Highly adaptive educational systems that respond to a student's individual state.
Wow.
Enhancing automotive safety by monitoring driver fatigue or distraction, and improving customer service interactions to be more efficient and perhaps more pleasant.
That sounds incredible, really potential life-changing technology.
Mm-hmm.
But you mentioned peril, the flip side.
Yes, the shadow side is significant and requires very careful consideration. The inherent complexities of emotion mean there's a high risk of misinterpretation by AI, and that can have severe consequences depending on the application, especially if important decisions are made based on inaccurate emotional assessments. Algorithmic bias, often stemming from unrepresentative or culturally skewed data, can lead to discriminatory outcomes, disproportionately affecting marginalized groups.
Right.
Collecting and analyzing sensitive emotional data raises profound privacy concerns and, in the wrong hands or context, can enable intrusive surveillance. And crucially, the capacity to recognize and respond to emotions creates a clear potential for emotional manipulation, whether for targeted commercial persuasion or, something potentially far more insidious.
This raises a really fundamental question we have to grapple with throughout this deep dive, I think. What does it even mean for AI to understand emotion in this context? Is it real understanding like ours, or is it just extremely sophisticated pattern matching?
That is the central philosophical question that underpins the entire field, and it's a distinction our sources highlight repeatedly. Current AI models are exceptionally good at learning complex patterns from vast data sets and classifying inputs based on the labels those patterns were associated with during training. So an AI system can identify a specific configuration of facial muscles as corresponding to the label joy, because it has learned to correlate that pattern with that label across thousands or millions of examples. But does that statistical pattern recognition equate to a genuine comprehension of the subjective felt experience of joy? The pioneers of affective computing, like BERT, even questioned whether computers could ever have emotions. While that specific question is perhaps less central now, the challenge remains. Bridging the enormous gap between technically classifying an observable signal and genuinely comprehending the subjective, rich, and highly context-dependent internal human state it might be associated with. Our sources make it very clear that current AI systems are, frankly, far removed from understanding emotion in anything like a human sense.
Okay, let's unpack this narrative then. It sounds like a complex journey with a lot of different threads, spanning decades of research and grappling with fundamental questions about what it means to be human and what it means for a machine to understand. How are we going to navigate this deep dive? What's the plan?
Good question. We've sort of set the stage now with the core concept, the historical roots in those early programs like ELIZA and Kismet, and that inherent tension between aspiration and utility.
Yeah.
Our roadmap now is to first look at the evolution of this field, particularly how it has been dramatically reshaped over the last decade or so by technological advancements. Then we'll dive into the current techniques AI uses, modality by modality, how it tries to decode signals from faces, voices, even physiology and text.
Okay.
After that, we'll explore the major conceptual and technical challenges that make this pursuit so difficult and, frankly, prone to error. And finally, we'll tackle the absolutely critical ethical debates surrounding this technology and its potential impact on society and, well, on ourselves.
And just a reminder for you listening, if you find this kind of deep dive valuable, exploring these complex topics, do consider subscribing to Silent Mind Studio and following us. We explore topics like this regularly. That sounds like a thorough plan. Let's jump into the first part then. The story of how this field has evolved over time, especially in the last decade. How did we get from ELIZA to where we are now?
Right, part one, the unfolding story. As we touched upon with ELIZA and Kismet, the journey of AI attempting to understand human emotions certainly has systemical depth. But our sources compellingly argue that its trajectory has been dramatically reshaped, specifically over the past decade, roughly from around 2014, let's say, to the present. This period wasn't just about steady progress. It was really defined by significant breakthroughs in machine learning, especially the rise of deep learning, coupled with the increasing availability of large data sets. This evolution reveals a fascinating and ongoing interplay between technological capability, shifting theoretical perspectives on the nature of emotion, and a growing recognition of just how profoundly complex human affect truly is.
So let's revisit those foundational seeds you mentioned earlier. Rosalind Picard's work seems pretty central to formalizing the field, putting a name to it.
Absolutely. Picard's foundational 1995 technical report and her subsequent 1997 book, Affective Computing, are widely credited with formally defining this area of research. Her core argument was, frankly, groundbreaking at the time, that for computers to be truly intelligent and interact effectively and naturally with humans, they would need the capacity to recognize, express, and potentially even have emotions. Her early vision foresaw applications across diverse domains, from improving learning experiences and information retrieval to enhancing artistic expression, supporting health and well-being, and creating more engaging human-computer interactions. Early projects like Kismet were tangible, physical attempts to demonstrate some of these initial ideas, building a machine that could look, listen, and respond in ways designed to feel social or emotional.
And these early efforts, they were heavily influenced by existing ideas about emotion from psychology, right? You mentioned Ekman.
Yes, profoundly so. A major influence came from psychological theories, particularly Paul Ekman's influential work on basic universal emotions. The idea that there are a few core emotions like anger, disgust, fear, happiness, sadness, and surprise.
The classic six.
The classic six, exactly. And that these are associated with distinct, universally recognizable facial expressions. Ekman and Wallace-Friesen's facial action coding system, or FACS, became a really foundational tool. FACS is a system for anatomically coding every observable human facial movement based on specific muscle contractions into action units, or AUS.
Clear.
Early facial expression recognition, FER systems, were often guided by this, attempting to detect specific AUs or classify static images or short video clips into these predefined basic categories.
Okay, so that provided a kind of framework, a starting point. Where did the last decade really see things leap forward? What was the catalyst?
That pivotal moment really arrived around 2014, marked by the widespread and incredibly successful application of deep learning techniques, particularly convolutional neural networks, or CNNs, for image-based tasks like facial recognition. This offered a fundamental shift in how AI processed visual data compared to the traditional machine learning approaches that came before.
How was it different? Like, what was the big change? Can you break that down?
Sure. Think of traditional machine learning before deep learning. Researchers and engineers had to manually design features that the computer would look for. For facial recognition, they might program the computer to detect things like the texture around the eyes using techniques like local binary patterns, LBP, or the distribution of edge directions, which is histograms of oriented gradients, or HOG.
Right, so humans telling the computer exactly what features matter.
Precisely. This required significant human expertise and effort to craft these specific features, and they might not always capture the most subtle or relevant information for emotion. Deep learning, specifically CNNs for images, changed this completely by enabling the models to learn relevant hierarchical features directly from the raw data from the pixels themselves in an end-to-end fashion.
So the AI basically taught itself what to look for in the image.
Yeah.
It figured out the important patterns on its own.
Exactly. You feed it thousands upon thousands of images labeled with emotions or action units, and the CNN architecture, through its multiple layers, automatically learns the complex combinations of edges, shapes, and textures that are most predictive of those labels. It essentially figures out how to spot an eyebrow furrow or the characteristic lines of a smile on its own, without explicit programming for those specific things. This breakthrough was both enabled by and fueled by the increasing availability of large-scale datasets. Datasets like FER 2013, although they had their own limitations, like often featuring posed or stereotyped expressions and noticeable demographic imbalances, which is crucial, they provided the sheer volume of data necessary to train these data-hungry deep learning models effectively. This period, from roughly 2010 into the late 2010s, saw an explosion in research interest in affective computing, largely powered by these deep learning advancements, showing significant improvements in accuracy for tasks like FER.
Okay, so deep learning really turbocharged facial expression recognition. That makes sense. But human emotion isn't just expressed on the face, is it? That seems like only one piece of the puzzle.
Not at all, and that's a crucial point the field quickly realized. As the capabilities for analyzing single modalities improved, researchers increasingly acknowledged a fundamental, undeniable aspect of human emotional expression: its inherently multimodal nature. We don't just use our faces to show emotion, we also use the tone and quality of our voice, our body language and posture, physiological changes in our body like heart rate or sweating, and of course the specific words we choose and how we structure them. Recognizing this crucial multimodal reality spurred the development of multimodal emotion recognition, or EMER, systems, becoming a major focus from the mid-2010s onwards. The goal was, and is, to integrate information from two or more of these channels, combining what the AI sees, hears, and reads to achieve a more robust, accurate, and nuanced understanding of a person's state. By around 2020, MER systems that combined inputs like facial expressions, vocal intonations, the sound of the voice, and text sentiment analysis, the emotion in the words, became much more common in research. The core technical challenge shifted significantly. It wasn't just about analyzing one signal well, but developing effective techniques for fusing information from these diverse sources.
Fusing, like blending them together.
Yeah.
Exactly. How do you combine data coming in from a camera, a microphone, and text analysis in a meaningful way? Researchers explored various strategies. Early fusion, combining the raw features before any interpretation. Late fusion, processing each modality separately and then combining the final decisions or scores. And more complex hybrid or model-based fusion techniques that might learn how to best weigh or integrate information from different channels. Our sources even mention approaches colloquially referred to as cold-blooded fusion, highlighting the complexity of truly blending these disparate data types effectively.
Cold-blooded fusion. That sounds
Yeah.
intense, maybe a bit detached, which is interesting given we're talking about emotion. So moving beyond just single signals to combining them, what was the next major step in this evolution? Where did the focus shift then?
The next evolution, starting in the late 2010s and continuing as a major frontier today, was a deeper appreciation for the absolute critical importance of context. Early AI systems tended to analyze isolated pieces of information, a single static image of a face, a short, decontextualized audio clip, a single sentence of text. But human emotions are rarely expressed in a vacuum. They are dynamic, they evolve over time, and they are profoundly influenced by the situation, the social dynamics, and, crucially, the flow of a conversation.
So recognizing emotion needs to consider the whole scene, the history, who you're talking to, what happened before.
Exactly. This led to a focus on multimodal emotion recognition in conversations, or MRC. These systems are designed to identify the emotional state associated with individual turns or utterances within a dialogue. But the key is that they do this by considering the interplay between the speakers, how a person's emotional state might be changing over the course of the conversation, the relationship between the speakers, and the overall subject matter and context of the dialogue. It's about understanding emotion and interaction. Alongside this shift towards understanding emotion in dynamic contexts like conversations, there's also been a push beyond classifying just a few predefined basic emotions. Researchers are increasingly interested in more fine-grained analysis, recognizing a wider spectrum of discrete emotions beyond the core six, understanding the continuous dimensional aspects of emotion, like how positive or negative a feeling is, valence, and how activated or energized it is, arousal, and crucially, identifying complex, blended, or mixed emotional states. These mixed states are far more common in real life than pure, prototypical basic expressions.
Like feeling that mix of sadness and warmth you get from nostalgia, maybe. Or being both excited and nervous about something. Those don't fit neatly into a single box like happy or sad.
Precisely. Those are exactly the kinds of nuanced states that earlier systems struggled with. And more recently, building on the success of large language models like GPT, we're seeing the emergence of multimodal large language models, or MLLMs. These models are designed to process and integrate diverse data types, text, images, audio, sometimes even video within a single massive framework. Our sources point to MLLMs holding considerable promise for complex tasks like MRC, given their potential for deeper contextual reasoning, integrating information across modalities, and understanding subtle nuances within complex interactions.
It really sounds like as the AI technology advanced, the applications of this emotion recognition capability also expanded significantly beyond just laboratory demos and research papers.
Absolutely. The past decade has witnessed a notable expansion in the development and, importantly, the attempted deployment of these technologies into real-world settings. We're seeing research and product development targeting healthcare applications such as potential tools for mental health diagnostics or monitoring patient states, in education with intelligent tutoring systems that try to monitor student engagement or frustration,
Right.
in retail, exploring ways to track customer emotions in stores or online, in human resources, attempting to analyze candidate effect during video interviews, and in automotive safety, using cameras and sensors to monitor a driver's state for signs of drowsiness or distraction. Our sources mentioned that by as early as 2023, several large retailers were already using or experimenting with AI facial emotion recognition in real time within their stores,
Oh.
ostensibly to potentially adapt service or product placement based on perceived customer mood.
That's actually happening now in some places. That feels very present.
Yeah.
Not just future tech.
Yes, the move from lab research to attempted commercial application has been rapid in certain sectors, definitely. So, to synthesize this evolution over the past decade, it's clearly not just been a simple linear march of better technology. It's been a constant dynamic dialogue between the development of increasingly sophisticated methods and a growing, sometimes forced appreciation for the sheer complexity and subtlety of human emotion. Early successes with classifying basic posed emotions in controlled lab environments fueled significant optimism. But as researchers ventured into analyzing spontaneous expressions, multimodal signals, and dynamic conversational interactions, the limitations of existing models became increasingly clear, particularly in handling subtlety, cultural variation, and the need for deeper contextual understanding. It feels like each step AI takes towards trying to understand emotion seems to reveal yet deeper layers of human complexity it needs to grapple with. This entire trajectory, from those early simple programs to today's complex deep learning systems, is also heavily shaped by the availability of data and computational power. That's undeniable. the deep learning boom wouldn't have happened without both powerful algorithms and large data sets like FER 2013.
Right, you need the fuel.
Exactly. The current push towards multimodal and contextual AI relies on even more complex and frankly harder to obtain dataset synchronized, conversational data captured in more naturalistic settings. Data quality and quantity remain a critical bottleneck for progress, and as we'll discuss in more detail later, data is also the source of many of the significant challenges, particularly regarding bias and generalizability across different populations and contexts.
So the overall trend isn't just about recognizing a few isolated feelings anymore, but trying to interpret the full spectrum of affective phenomena as they unfold in dynamic, real-world contexts, moving towards a richer picture.
Exactly. The future aspiration, as suggested by the research directions in our sources, like MFCC, fine-grained analysis, and MLLMs, is a shift from simply labeling an emotion like sadness to potentially inferring its intensity, understanding what might have caused it in a specific context, predicting how it might influence subsequent behavior, and appreciating its interplay with the cognitive and social environment. However, this very aspiration immediately brings us back to that central conceptual question about what AI understanding truly means, and it raises significant conceptual and ethical implications that are still intensely debated.
Fascinating. It's clear the field has come a long way in a relatively short time, really pushed by technological leaps and a growing, if sometimes challenging, awareness of just how complex emotion really is. Now that we've seen the evolution, tracing the journey from early programs to multimodal systems, let's get into the nitty-gritty. How exactly do these AI systems try to decode human feelings? Using these different signals, faces, voices, bodies, text, what are they actually doing? And remember, if this detailed exploration is sparking your interest, subscribing to Silent Mind Studio helps us continue creating content like this. Okay, part 2, decoding feelings. We've traced this story from ELIZA to MLLMs, seeing how technology and a growing appreciation for complexity have shaped the field. But the practical question remains, how does AI actually look for and interpret emotion and signals as intricate as a human being? What are the core techniques it uses across those different modalities, face, voice, physiology, text?
Right, that's the focus for this section. It involves a diverse array of computational techniques, often drawing inspiration from psychological and neuroscience theories, leveraging machine learning to identify patterns within different data types that are thought to be indicative of affective states. Let's start with facial expressions, or facial expression recognition, FER. This has historically been one of the most dominant areas, largely because faces are such a prominent and readily observable channel of nonverbal communication. As we mentioned, much of this work is theoretically rooted in Paul Ekman's idea of basic universal emotions linked to distinct facial movements. Systems often try to detect specific facial muscle contractions, known as action units, AUS, from FACS, or more commonly now, classify the overall facial configuration into discrete emotional categories like happy, sad, angry, etc.
And the AI techniques for doing this, how do they look at a face and decide happy or sad?
Well, they've evolved significantly. Early approaches used traditional machine learning algorithms like support vector machines, SVMs, or multi-layer perceptrons, MLPs. These were fed with carefully designed, handcrafted features that engineers extracted from images, things like local binary patterns, LBP, for texture, or histograms of oriented gradients, HOG, for edge direction.
Okay.
But the field was really revolutionized by the deep learning shift. Convolutional neural networks, CNNs, became dominant. Instead of needing handcrafted features, CNNs automatically learn complex, hierarchical features directly from the raw pixel data.
Right, the self-teaching aspect.
Exactly, leading to much higher accuracy in recognizing intricate facial patterns. More recently, architectures like vision transformers, VITs, adapted from language processing models, are also showing promise in analyzing facial images. These techniques might focus on geometric aspects, the shape and relative position of facial landmarks like eyebrows, eyes, and mouth, or appearance aspects, looking at the texture, wrinkles, or bulges caused by muscle movements. Deep learning models often implicitly learn features that capture both.
And they train these models on vast data sets of faces with labels. Like this face is happy, this one is angry.
Exactly. Training requires large data sets of facial images or videos labeled with emotion categories or action units. Examples include datasets like FR 2013, KDEF, CK+R, and more recent, larger ones like AffectNet and RAFDB. A real-world application we see, as mentioned, is in some retail environments or audience analysis, where systems scan customer faces in real time to attempt to gauge aggregate emotional responses, though this practice is, as we'll discuss, ethically debated. Okay, moving on to the voice. Speech is another incredibly rich channel for emotion, and it's not just about the literal words spoken, but how the paralinguistic features. This is the domain of speech emotion recognition, or SER. The core idea here is that prosody aspects of speech, like its quality, intonation patterns, rhythm, loudness, and rate, carry strong cues about a speaker's emotional state, often independently of the semantic content, the words themselves.
So the AI is listening to the sound itself, the music of the voice, not just processing the text transcript.
Precisely. SER systems work by extracting specific acoustic features from the audio signal. Think of it like quantifying the musicality or texture of the voice. This involves features like male frequency substral coefficients, MFCCs, which essentially break down the sound into its fundamental frequency components, pitch features that capture the melody and contour of the voice, like how much it goes up and down, measures of energy or loudness, and parameters describing the voice's quality, like jitter or shimmer, which relate to voice stability. These are all quantitative ways to represent the sound of speech beyond the words. These acoustic features are then fed into machine learning models trained to classify them into emotional categories. Traditional models included things like Gaussian mixture models, GMMs, or hidden Markov models, HMMs, which are good for sequences. However, deep learning is now increasingly prevalent here too. Recurrent neural networks, RNNs, especially variants like LSTMs and GRUs, are well suited for processing the sequential nature of speech over time. CNNs can also be used by treating visual representations of sound, like spectrograms, as images. And hybrid architectures combining CNNs and RNNs are common to capture both local patterns in the sound and how they change over time.
What kind of data trains these voice-based systems, recordings of people sounding emotional?
Yes, datasets like RAVDES, IEMOCAP, EMODB, and SAVE, which contain recordings of speakers expressing different emotions, often actors, are used for training. SR faces significant challenges like background noise, which is ubiquitous in real life, the immense variability between speakers due to factors like age, gender, or accent.
Everyone sounds different.
Exactly. And the complex interplay between emotional tone and linguistic content, especially in phenomena like sarcasm, where the tone might completely contradict the literal meaning of the words. You might encounter this technology in call centers analyzing customer emotions to, say, route calls or adapt agent scripts based on perceived frustration or satisfaction.
That makes sense. Okay, faces, voices. What about sensing emotion from within the body itself? You mentioned physiological signals. That sounds more direct somehow.
Physiological signals offer a potentially more direct window into internal emotional responses because they're governed by the autonomic and central nervous systems, which operate largely involuntarily. A key advantage often cited for these signals is their potential objectivity. They're generally harder to consciously manipulate or socially mask compared to facial expressions or vocal tone. You can choose to smile when you're sad, but it's harder to consciously control your heart rate variability or skin conductance.
Okay, interesting. What kind of body signals are we talking about, and what do they supposedly tell us about emotion?
Well, there's quite a variety. Electroencephalography, or EEG, which measures electrical brain activity via electrodes placed on the scalp. EEG has excellent temporal resolution, meaning it can capture the rapid dynamics of neural activity related to emotion.
So fast changes in the brain.
Exactly. Though determining the precise location in the brain where the activity originates can be limited, and the signals are notoriously prone to noise from things like eye blinks or muscle movements requiring complex processing. Deep learning models like CNNs, RNNs, graph convolutional networks, GCNs, and even capsule networks are being explored to classify emotional states from these complex EEG patterns. Other signals include electrocardiogram or ECG, measuring heart activity. Features extracted from ECG, like heart rate itself, and especially heart rate variability, HRV, which is the variation in time between heartbeats, are well-established indicators linked to arousal, stress, and even specific emotional states like fear or relaxation.
Right, like fitness trackers measure HRV.
Exactly. That technology is becoming more common. Then there's galvanic skin response, or GSR, also known as electrodermal activity, or EDA. This measures changes in skin conductivity due to sweat gland activity. It's a common and relatively easy to measure indicator of physiological arousal or activation, often associated with emotional intensity or stress. Other signals like respiration rate, skin temperature, blood volume pulse, often measured with PPG sensors like those in smartwatches or fitness bands, and electromyography, EMG, which measures muscle activity. Even subtle, non-visible facial muscle movements are also utilized in research.
So the body gives off a lot of potential, maybe harder to fake emotional cues, but collecting them sounds more involved, maybe more invasive than just using a camera or mic.
It often is. While datasets like Deep, Amigos, and Mashnobe HCI exist, collecting clean, synchronized physiological data, especially signals like EEG, can require specialized equipment and expertise. This makes it less scalable for widespread, passive monitoring compared to faces or voice. Challenges include invasiveness or cumbersomeness, depending on the sensor. Wearing an EEG cap isn't exactly casual. Signal noise and artifacts, significant variability in physiological responses between individuals.
We all react differently.
Very differently. And the high computational cost of processing some signals like fMRI, functional magnetic resonance imaging, which measures brain activity via blood flow, makes it impractical for real-time use. Plus, it has lower temporal resolution compared to EEG, meaning it's slower to detect rapid changes. Despite these challenges, applications are emerging, particularly in healthcare, like wearable stress monitors using HRV and GSR, or in research involving effective brain-computer interfaces leveraging EEG, perhaps for therapy or communication aids.
Okay, so a more direct signal, but harder to get. And then there's text. With the explosion of digital communication, social media, reviews, emails, messages, analyzing emotion in written words must be a huge area.
Absolutely. Natural language processing, or NLP techniques, are fundamental here, especially given the sheer volume of text data generated constantly. The underlying theory is that the specific word choice, sentence structure, punctuation, use of emojis, and overall style of writing can reflect underlying emotional states, sentiments, or opinions.
How do they analyze text for emotion? Is it just looking up words in a dictionary, like happy is positive, sad is negative?
That's one early approach, but it's much more sophisticated now. Lexicon-based methods do exist, relying on dictionaries where words are pre-scored for sentiment or emotion associations, like CentiWordNet or LIWC. They infer emotion based on the presence and scores of words in a text. Traditional machine learning also used classifiers trained on features extracted from text, like bag of words counts, just counting word occurrences, or TF-IDF scores, which measure how important a word is in a document relative to a larger collection of documents. But deep learning models have really revolutionized this area as well. Recurrent neural networks, RNNs, like LSTMs and GRUs, are good at processing the sequential nature of text. Understanding word order matters. CNNs can capture local features like n-grams, short sequences of words. But the most significant advancement came with transformer models you've likely heard of, BERT GPT, and models specifically tuned for social media like Deepmoji. These models are incredibly powerful at capturing deep contextual relationships between words across longer distances in text, understanding nuance much better. These techniques are applied to various tasks, classifying overall sentiment, positive, negative, neutral, categorizing text into discrete emotion labels like anger, joy, sadness, identifying tricky things like sarcasm or irony, and even trying to pinpoint the cause or target of an emotion mentioned in the text, e.g. I'm angry at the company because of the delay. Datasets often come from annotated social media posts, product reviews, or datasets curated for specific NLP research tasks like SemEval.
What makes text analysis for emotion particularly tricky? Language seems so slippery.
It is. Language itself is inherently ambiguous. Words can have multiple meanings depending on context. Sarcasm, irony, and figurative language like metaphors are particularly challenging because the literal meaning often contradicts the intended emotional meaning.
Yeah, great job can mean very different things.
Exactly. The role of broader context beyond the immediate sentence is critical, but hard for AI to capture fully. Cultural nuances in language use, idioms, slang, and simply the sparsity of data for expressing less common or very subtle emotions in text are also significant difficulties. Despite these challenges, applications like AI chatbots using sentiment analysis to tailor their responses for better customer service are becoming increasingly common and visible.
So we have AI trying to decode signals from faces, voices, bodies, and text. Given that humans rarely use just one of these channels to express how they feel, we're usually doing several at once, bringing them all together in multimodal recognition seems like the obvious, necessary progression, right?
Absolutely. Multimodal emotion recognition, or MER, is the logical next step, aiming for a more holistic, accurate, and robust assessment by integrating information from multiple modalities simultaneously. The core rationale is that combining cues from, say, face, voice, and text can help overcome the limitations or ambiguities of any single channel and provide a richer, more nuanced picture of a person's state. For instance, An ambiguous facial expression, maybe a slight smile, might be clarified significantly by the tone of voice. Is it warm or sarcastic? Or the accompanying words.
And how do they manage to combine all that very different information, image pixels, audio waves, text sequences? That fusion process sounds complicated.
It is the significant technical challenge of fusion. Techniques range in complexity. Early fusion methods simply combine the raw features extracted from different modalities before feeding them into a single classification model. Decision-level or late fusion methods process each modality separately using specialized models, and then combine the final predictions or scores using methods like voting, averaging, or training another model, a meta-classifier, to make the final decision based on the individual modality predictions. More complex hybrid or model-based fusion techniques are increasingly used, often within deep learning architectures. These can involve mechanisms like attention, where the model learns to dynamically weigh the importance of information from different modalities based on the current context, maybe paying more attention to the voice if the face is obscured, for example. The advent of transformer-based architectures and multimodal large language models, MLLMs, is particularly promising here, as they were designed from the ground up to process and integrate multiple data streams within a unified framework, holding potential for more sophisticated cross-modal understanding, especially in dynamic settings like conversations. MER is particularly relevant for applications requiring rich, interactive understanding, such as advanced conversational AI that needs to track user state, assessing mental health in virtual environments or through telehealth, creating more engaging and adaptive educational tools, or sophisticated driver monitoring systems that might combine facial cues of drowsiness with vocal stress indicators or physiological signals like heart rate.
What makes MER particularly challenging, beyond the issues with each individual signal type?
Well, beyond the challenges inherent in each individual modality, noise, ambiguity bias, combining them introduces new layers of complexity. How do you effectively align and synchronize data streams that might have very different temporal resolutions, a continuous audio wave, a sequence of discrete video frames, individual text utterances, slow-changing physiological signals? Getting the timing right is crucial.
Yeah, that sounds tough.
Developing the optimal fusion strategy, knowing how to best combine the information for a given task and context, is still an active research area. There's no single best way. How do you handle situations where one or more modalities are missing or noisy? What if the camera is blocked or the microphone picks up interference? And simply the computational complexity of processing and integrating multiple data streams simultaneously is much higher, requiring more powerful hardware. True cross-modal reasoning, understanding how information from one channel interacts with or influences information in another, is also a very difficult problem that current models are still grappling with.
So bringing it all together seems powerful, but adds significant layers of technical and conceptual difficulty. And you mentioned earlier, across all these modalities, whether single or combined, there's this fundamental issue of ground truth. What exactly does the AI learn from?
Yes, this is a persistent and critical issue that runs through the entire field, a real foundational problem. AI models, regardless of modality, are trained on data that has been labeled with emotional categories. But these labels, especially for modalities like faces and voices in many commonly used datasets, are often based on external human perception or annotation of an expressed emotion, not necessarily the person's internal affective state.
So what someone looks like they're feeling, not what they are feeling.
Potentially, yes. Datasets where actors are instructed to portray specific emotions, like in RAVDAS or parts of CK+, are prime examples of this. The AI learns to recognize a posed, perhaps exaggerated expression, which may differ significantly from a spontaneous, subtle, real-world display of that same emotion. While physiological signals are often considered potentially more objective because they are harder to fake, they still require human interpretation to link a specific signal pattern, like increased heart rate and skin conductance, to a specific emotional state. Is it excitement, fear, anxiety, or just physical exertion? This highlights a complex relationship between observable signals, the interpretation applied to them, offered by human labelers, and the presumed internal feeling, suggesting a potential hierarchy of objectivity or directness among modalities that current AI models may not fully capture or differentiate.
And there seems to be a constant trade-off here, too, between how rich or potentially objective a signal is, like brain activity, and how practical or scalable it is to measure in the real world.
It's exactly that trade-off. Measuring detailed brain activity with EEG might offer deep insights into the neural correlates of emotion, but it requires specialized, often cumbersome equipment, making it less scalable for everyday use compared to analyzing text from social media or capturing a face with a standard camera or smartphone. Faces and voice are non-invasive and ubiquitous, but they are susceptible to conscious masking, cultural display rules, and environmental noise.
Right.
Text is abundant and easily collected digitally, but it's inherently ambiguous and heavily context-dependent, lacking the nonverbal cues. Multimodal systems attempt to strike a balance by combining sources, hoping the strengths of one modality can compensate for the weaknesses of another. But as we noted, fusion adds its own set of complexities and computational costs. Furthermore, the very choice of which psychological model of emotion to build upon, whether you focus on Ekman's discrete basic emotions, which have dominated many data sets due to the relative ease of using tools like FACS for labeling observable muscle movements, or adopt a dimensional model focusing on valence and arousal, profoundly shapes the techniques used, the type of data collected, and ultimately what the AI learns to recognize. The historical dominance of basic categories and datasets has arguably constrained the scope of emotion AI, making it struggle particularly with the subtle, mixed, or culturally specific ways emotions are actually expressed in the messy real world.
It sounds like the how is incredibly sophisticated, drawing on techniques from many different fields and analyzing multiple signals. But it's also layered with significant complexities, compromises, and fundamental assumptions about the nature of emotion itself. This brings us very clearly to the major challenges that seem to stand in the way of AI achieving anything close to true emotional understanding. Let's delve into those difficulties next in Part 3. And as we move into these challenges, remember, if you appreciate these deep dives, subscribing to Silent Mind Studio helps us keep making them.
Right. Part 3, the labyrinth of effect. Despite the impressive technical progress and the development of sophisticated techniques across various modalities that we've just discussed, AI's journey into understanding human emotions is definitely navigating a labyrinth filled with formidable obstacles. Our sources consistently highlight that the path is fraught with major challenges, stemming not only from technical limitations, but also, crucially, from the inherent nature of emotion itself. Persistent limitations in data, algorithmic biases, and the sheer variability and complexity of human expression.
And the first and perhaps most fundamental difficulty seems to be the elusive nature of emotion itself. Its subjectivity, its ambiguity, the fact that there's no single clear definition among humans, right?
Absolutely. At the very heart of the challenge is the lack of a universally agreed upon scientific consensus within psychology and neuroscience on what an emotion is, precisely how many distinct emotions exist, or how they should be consistently defined and categorized across different theories. This foundational ambiguity directly impacts the AI field because AI systems, especially supervised learning models, require structured definitions and clear categories to learn from effectively.
So AI researchers basically have to pick a side, choose which psychological theories of emotion to build their systems on, even though the scientists themselves don't fully agree on the right model.
Exactly. The field is constantly navigating competing theoretical frameworks. There are discrete emotion theories, heavily influenced by Ekman, which propose a small, finite set of basic universal emotions, each supposedly with distinct behavioral and physiological signatures. On the other hand, dimensional models view emotions not as separate categories, but as lying along continuous axes, such as valence, how positive or negative a feeling is, arousal, how activated or intense it is, and sometimes dominance, how in or out of control someone feels. AI systems built based on a discrete model will approach the problem differently and require different labeled data compared to systems built on a dimensional model. A significant challenge here is recognizing complex, mixed, or subtle emotions. Think again of feelings like bittersweetness, nostalgia, confusion mixed with frustration, or mild irritation, which are incredibly common in daily life, but don't fit neatly into predefined basic categories and are often significantly underrepresented or even absent in available training datasets. Furthermore, while incredibly influential, Ekman's universality hypothesis regarding distinct universal facial expressions is facing increasing scrutiny in psychological research. Critics argue that emotional expressions are far more context-dependent, flexible, and culturally variable than the original theory suggested. The assumption of a rigid one-to-one mapping between a specific facial configuration, like a specific smile type, and a single specific emotion, like happiness, is increasingly seen as an oversimplification, potentially a dangerous one. Cultural variation in how emotions are displayed and interpreted, known as display rules, can significantly obscure the interpretation of AI systems when deployed across different cultures. users. The widely reported discontinuation of Microsoft Azure's facial emotion recognition program, partly citing concerns about its potential for discrimination and stereotyping based on this kind of potentially oversimplified interpretation of facial cues, really underscores the real-world consequences of this conceptual challenge.
So what looks like a specific expression, say a smile, in one culture or situation might mean something completely different somewhere else. And the AI, trained on one set of assumptions, might totally miss that nuance or misinterpret it.
Precisely. And it's not just cultural variation between groups. There's immense inter- and intra-individual variability. People express and experience emotions differently based on their unique personality, their cultural background, their upbringing, their immediate mood, their physiological state, and even how they think they should express themselves in a given situation. And the same individual might express the same underlying emotion differently at different times or in different contexts throughout the day. AI systems, often trained on aggregated data designed to find common patterns across many people, really struggle to account for this rich and complex individual variability and authenticity. And this brings us back to that critical distinction you raised earlier, the difference between outward expression versus true internal feeling. This is a challenge AI often fundamentally misses or ignores. An outward display isn't always a direct, transparent window into the internal state. A smile can be genuine happiness, but it can also be politeness, a social mask to hide discomfort or sadness, or even a nonverbal sign of contempt or dismissal depending on the person and the context.
Right, the customer service smile.
Exactly. Current AI systems primarily learn from observable expressions and have very limited capacity to infer the authenticity or the underlying motivation behind those displays, let alone the deeply subjective feeling itself. Beyond the inherent ambiguity and subjectivity of emotion itself, we face significant data dilemmas. Data is often called the fuel of modern AI, but in affective computing, it's frequently also a major source of flaws and limitations. The performance and generalizability of these models depend heavily on access to large, high-quality, and truly representative data sets.
But obtaining that kind of data labeled with nuanced emotions from real-world interactions reflecting diverse people sounds incredibly difficult, expensive, and potentially invasive.
It is. On all counts. There's a persistent need for large, diverse, and crucially ecologically valid data that truly captures how emotions are expressed and experienced in natural, real-world situations, not just controlled lab settings or staged performances by actors. Many existing datasets are relatively small, were collected in labs, primarily feature posed or acted emotions rather than spontaneous ones, or significantly lack demographic diversity in terms of race, age, gender, cultural background. Most focus on a limited set of basic, prominent emotions, with complex, nuanced, or subtle states like confusion, relief, embarrassment, nostalgia, being significantly underrepresented if present at all. Obtaining sizable, diverse, real-world datasets suitable for training complex emotion recognition systems, especially multimodal ones that need synchronized video, audio, maybe text, maybe physiology, is particularly daunting due to the complexity and cost of synchronized capture and the difficulty of nuanced annotation. And that brings us directly to the annotation problem. Labeling emotional data, whether it's facial expressions, vocalizations, or text, is an inherently subjective process. Different human annotators, even trained ones, will inevitably perceive and label emotions differently based on their own cultural background, personal experiences, biases, and even their understanding of the specific emotion categories they're supposed to be using. This leads to inconsistencies and often low inter-rater reliability, meaning different labelers don't agree. There's a known issue of observer bias, where features of the person being observed, like their race or gender, or the annotator themselves, like their cultural background or gender, can unconsciously influence the emotional label assigned. Furthermore, this annotation process is incredibly time-consuming, labor-intensive, and expensive, particularly for multimodal data that requires synchronized, frame-by-frame, or utterance-by-utterance labels across different channels. We also face serious issues with imbalanced datasets. Some emotional states, like general happiness or neutrality, are far more frequently expressed and therefore much more represented in data sets than less common or perhaps less socially acceptable emotions like disgust, fear, or intense sadness. Training models on such imbalanced data inevitably leads to systems that might be quite good at recognizing the common emotions, but perform poorly and unreliably on the minority classes, the less frequent ones.
Right. They just don't see enough examples.
Exactly. Analysis of widely used datasets like AffectNet and XPW has clearly revealed not only emotional imbalances, but also significant demographic imbalances, contributing heavily to the biases we're about to discuss.
This links directly, as you said, to the critical challenge of bias in the code and the data that feeds it. This isn't just a technical glitch, it's a major ethical problem, too.
Absolutely. Algorithmic bias is a pervasive issue across AI, but it's particularly critical and potentially harmful in emotion recognition because it directly impacts how people are perceived and potentially treated based on incredibly personal data. AI models trained on biased data inevitably inherit and can even amplify societal biases related to gender, race, cultural background, age, and neurodiversity. This isn't just a technical bug, it's a profound ethical issue with real-world consequences leading to discriminatory outcomes.
Like systems being less accurate for certain groups of people, failing more often for some than others.
Exactly. Studies have documented performance disparities where emotion recognition systems are demonstrably less accurate for individuals with darker skin tones compared to lighter ones, or where the same neutral expression on a black face is more likely to be misinterpreted as anger compared to a white face, or where a smile from a woman might be interpreted differently than the same smile from a man, reflecting societal gender biases embedded in the data or labels. These biases fundamentally stem from the underrepresentation, misrepresentation, or skewed labeling of these demographic groups and cultural expressions in the training datasets. When such bias systems are used in high-stakes applications like hiring, security screening, or healthcare, they can perpetuate systemic inequalities and lead to unfair treatment. Vulnerable populations, such as neurodiverse individuals who may express emotions differently, the elderly, or children, are particularly at risk because their expressions might deviate from the norm baked into the training data, or they may be significantly underrepresented, leading to higher misinterpretation risks and potentially inappropriate or harmful responses from AI systems interacting with them. Another major challenge, which we touched on earlier when discussing evolution, is what our sources call the neglected nuance. The difficulty AI has with contextual understanding. Emotions are deeply embedded in context, but current AI often struggles to incorporate this understanding effectively, treating signals in isolation.
Yet you really can't understand why someone is crying without knowing if they just won an award or received terrible news. The context is everything.
Precisely. The meaning of an emotional display changes dramatically depending on the surrounding situation. A tearful expression could signify sadness, overwhelming joy, deep frustration, or even physical pain. A smile in a relaxed social gathering means something different than a smile during a tense negotiation or while delivering bad news. AI systems that analyze expressions or vocal tones in isolation without understanding the broader situational context are highly prone to making serious errors in interpretation. Similarly, in dynamic conversations, emotions are not static. They are relational and evolve over time. They are influenced by previous turns in the dialogue, by the emotional states and responses of other speakers, by the shared history between the participants, and by the overall goals and subject matter of the conversation.
Right, it's a back and forth.
Exactly. Effective recognition in conversations, MRC, requires sophisticated models that can track these dependencies, understand the interplay of emotions within the flow, and integrate linguistic and non-linguistic context over time. Capturing these temporal dynamics, how emotions unfold, build, or dissipate over time with varying intensity and duration, is also crucial for genuine understanding, but technically very challenging.
And for many of these potential real-world applications, all of this sophisticated analysis, multimodal, contextual, trying to avoid bias, needs to happen incredibly quickly, in real time.
That's the speed imperative, another big hurdle. Applications like intelligent tutoring systems needing to respond immediately to a student's frustration, driver monitoring systems needing to detect drowsiness or sudden stress instantly, or mental health support tools providing real-time feedback require very fast inference times. However, sophisticated deep learning models, especially complex multimodal and contextual ones that process multiple data streams and incorporate history, are computationally intensive. They need a lot of processing power. This high processing cost can hinder their deployment on resource-constrained devices like smartphones, wearables, or standard in-car systems. Furthermore, the impracticality of using some informative modalities like fMRI for continuous real-time monitoring limits the depth of physiological data that can be used in many practical applications that need instant results. Finally, there's the issue of peeking into the black box, the significant challenge of interpretability and explainable AI, XAI. Many advanced AI models, particularly large, deep neural networks like the ones often used now, are frequently described as black boxes. Their internal decision-making process, how they arrive at a specific classification or prediction from the input data, is opaque and difficult for humans to understand or trace.
And why is that particularly problematic for AI that's trying to interpret something as personal and complex as human emotion? Why do we need to see inside?
Because of the potentially high-stakes nature of applications. If an AI makes an assessment about someone's emotional state that could have significant consequences for them in forming a mental health diagnosis, influencing an employment decision, affecting a legal judgment, or triggering an intervention in a safety-critical system like a car, it is absolutely crucial to understand why the system reached that particular conclusion. Without transparency into the AI's reasoning, it's incredibly difficult to build trust in the system, to diagnose when and why it might be making errors, especially subtle ones, or to identify and mitigate biases effectively.
Right, you can't fix a bias if you don't know why it's happening.
Exactly. If a black box model is exhibiting biased behavior, misinterpreting the emotions of a certain demographic or cultural group, diagnosing why this is happening, is it an issue with the specific data it saw, the model architecture itself, or specific biased features the model learned to rely on, is extremely hard, hindering efforts for fairness and accountability. Explainable AI, XAI methods, aim to provide this transparency, but applying them effectively to complex, multimodal affective computing models is still an active and challenging area of research. And as our sources highlight, these challenges are deeply interconnected and often reinforce each other. The historical reliance on potentially oversimplified psychological models of emotion, addressing the elusive nature of emotion itself, has directly contributed to the creation of flawed and unrepresentative data sets, the data dilemmas, which in turn feed into and perpetuate algorithmic biases, bias in the code. Models trained on this limited or biased data struggle inherently with the richness, variability, and real-world nuance of human expression and context, the neglected nuance. Furthermore, the scientific quest for objective, measurable signals often clashes with the fundamentally subjective experience of emotion itself. AI processes objective data pixels, audio features, physiological readings, but inferring a subjective feeling from that remains a core conceptual challenge. Even physiological signals, while harder to fake, require complex interpretation. An increased heart rate isn't just one emotion, it could be many things.
And the black box nature of the AI makes it even harder to understand and address these biases and figure out why misinterpretations are happening, especially for vulnerable groups who are already at risk of being misunderstood or misrepresented by the system.
Precisely. Without understanding the steps the AI takes to arrive at an emotional classification, debugging biased behavior and ensuring equitable performance across diverse individuals and contexts becomes a daunting, sometimes seemingly impossible task. These multifaceted challenges collectively reveal the deep complexities that make the path to anything resembling genuine emotional understanding by AI a truly significant and perhaps fundamentally limited undertaking, at least with current approaches.
It certainly sounds like navigating a complex labyrinth, filled with conceptual data and algorithmic hurdles. And with all these technical and conceptual challenges in trying to build these systems, we haven't even really begun to properly discuss the profound ethical debates this technology ignites. This must be an absolute minefield given the intensely personal and sensitive nature of emotion. Let's delve into that next in our final part. And one last reminder, if you're finding value in understanding these complex layers, subscribing to Silent Mind Studio ensures you won't miss future explorations.
Right. Part 4, the moral compass. We've covered the evolution of AI emotion recognition, seen the techniques it uses across different human signals, and explored the significant technical and conceptual hurdles that make this pursuit so difficult. Now, we absolutely have to address the profound ethical debates and societal questions raised by AI designed to recognize and potentially respond to human emotions. As our sources make very clear, the potential for misuse, the impact on individual autonomy and dignity, and the broader consequences of embedding emotionally aware technologies into the fabric of our lives are critical concerns that demand careful, ongoing consideration. At the very forefront of these concerns, perhaps unsurprisingly, is the issue of privacy and data security. Emotional data is extraordinarily sensitive and intimate information. It reflects our inner lives, our vulnerabilities, our personal experiences. Our sources conceptualize this type of data as akin to mental data, fundamentally linked to our identity, our personal autonomy, and even our basic freedom of thought.
Mental data, that's a powerful framing.
It is. Public perception often views this kind of data as uniquely personal and potentially highly susceptible to manipulation if not handled with the utmost care and respect.
And the worries are about how this deeply personal data is collected, stored, and ultimately used. Who gets to see it?
Exactly. Significant ethical concerns arise about passive collection capturing emotional data via cameras in public spaces, microphones in smart devices, sensors in cars or wearables, potentially without someone's full, active, informed awareness or genuine consent. How is this intimate data stored securely? Who has access to it? How is it processed and analyzed? Is it shared with third parties or potentially sold for commercial purposes? The risk of data breaches involving emotional data or the misuse of this intimate information by unauthorized parties could have severe and deeply personal consequences, ranging from embarrassment and reputational damage to targeted manipulation, profiling, or discrimination based on perceived emotional states. There's also a concept our sources discuss, which is quite chilling: the loss of ephemerality. Fleeting emotional expressions, a momentary sigh of relief, a quick frown of confusion, a blush of embarrassment, which were once transient moments in human interaction, vanishing almost as soon as they appeared.
Yeah, they just happen and disappear.
Can now be captured, digitized, stored indefinitely, and reanalyzed repeatedly in the future by algorithms. Who controls this permanent record of our momentary, often involuntary states? What are the implications when what was once fleeting becomes a permanent data point, potentially used out of context later?
This leads very naturally into concerns about surveillance and potential control. If AI systems can constantly monitor our emotional states, maybe in the workplace, in schools, or even in public, it feels like it creates a powerful new pathway for surveillance, which could potentially stifle genuine human expression and authenticity.
It absolutely opens that door, and it's a major area of ethical tension highlighted in the sources. Consider the potential implications in the workplace. Emotion recognition technology, ERT, is being explored and, in some cases, reportedly deployed in areas like recruitment.
During interviews.
Yes. To assess the perceived emotional suitability or stress levels of candidates during video interviews. It's also discussed for monitoring current employees, perhaps attempting to gauge productivity, engagement, stress levels, or even detect potential signs of workplace conflict or harassment based on facial or vocal cues. While proponents might argue these systems could offer benefits like identifying burnout early, these applications raise very serious concerns about intrusive and potentially exploitative surveillance, creating pressure on employees to perform or suppress certain emotions to fit algorithmic expectations, and fundamentally eroding trust and dignity in the workplace. Even when organizations claim to obtain consent, the inherent power imbalance in an employer-employee relationship makes the voluntariness and informed nature of that consent highly questionable.
And in education, you mentioned monitoring students. That feels similarly fraught.
It is. Similarly, AI systems are being developed and tested in educational settings to monitor student engagement, attention levels, and emotional states during online learning or even in physical classrooms via cameras. The stated goal is often benevolent to personalize learning experiences, adapt teaching methods in real time, or identify students who might be struggling, disengaged, or need additional support. However, this also risks creating a chilling effect where students feel they are constantly being watched and evaluated based on their expressions, potentially suppressing natural expressions of confusion, frustration, or boredom for fear of being judged negatively by the system or the educator using it. It can fundamentally redefine the student-educator relationship, shifting it towards a dynamic where the student feels more like a data provider whose internal state is being constantly analyzed, rather than a learner engaging in a supportive environment. The subjective feeling of creepiness is also a significant factor for many individuals subject to this kind of monitoring. And then there is the highly controversial potential application of ERT in public spaces and policing. This includes speculative ideas like attempting to predict criminal behavior based on observed emotional states in crowds, or using AI to detect deception during interrogations or security screenings at airports.
That sounds very problematic.
Extremely. Given the current limitations in accuracy that we've discussed, the high potential for bias, especially against certain groups, and the fundamental lack of scientific consensus on reliably linking external expressions to internal states like deception, using these systems in such high-stakes scenarios raises grave concerns about misidentification, potential wrongful accusations, and profound clashes with fundamental human rights and civil liberties in democratic societies. The idea of an AI system flagging someone as suspicious based on a potentially misinterpreted expression during a stressful public situation is deeply unsettling and ethically dubious.
So the fear isn't just about the data privacy itself, but about how this pervasive surveillance could actually change our own behavior and interactions, make us less authentic.
Exactly. The overarching fear with the potential for widespread emotional surveillance, whether at work, school, or in public, is that individuals will consciously or unconsciously alter, suppress, or mask their natural emotional expressions to conform to perceived algorithmic expectations or to avoid scrutiny or negative algorithmic judgments. This pressure towards emotional conformity can foster inauthenticity, reduce individual autonomy in how we choose to present ourselves to the world, and add an additional psychological burden of constantly managing one's external emotional display to meet the perceived demands of unseen algorithms. Related closely to surveillance but distinct is the potential for emotional manipulation and persuasion. AI systems that can recognize or infer emotional states or even subtle shifts in mood possess a powerful potential to influence human behavior, choices, and opinions, often in ways that are subtle or covert, operating below the level of conscious awareness. This capability is, understandably, highly attractive in domains like marketing, advertising, and even political campaigning.
Like using AI to detect you're feeling vulnerable or stressed, and then showing you targeted ads for, I don't know, comfort food or a loan, designed specifically to exploit that detected emotional state.
Yes, precisely that kind of scenario. Tailoring advertising content, product recommendations, or even the timing of delivery based on a detected mood, potentially exploiting moments of sadness, stress, boredom, or insecurity, crosses an ethical line for many observers and raises questions about predatory practices. While an application like an AI tutor adapting its pace because it senses a student's frustration might be seen as a benign or even helpful use of detecting emotional states, the same underlying technology and principles could be used for unethical manipulation on a much larger scale. Where is the ethical line between helpful adaptation to a user's state and exploitative influence? Vulnerable individuals or populations may be particularly susceptible to such tactics, raising the ethical stakes even higher.
And we need to circle back to bias, fairness, and discrimination again, but framed now squarely as a central ethical issue stemming from these capabilities, not just a technical one.
Yes, absolutely. Algorithmic bias, which we discussed as a major technical challenge, is fundamentally a profound ethical issue in effective computing with direct consequences for justice and equity. AI models, because they are trained on data that reflects and often inherit societal biases related to gender, race, culture, age, disability, and neurodiversity, can perpetuate and even amplify these biases when deployed in the real world. This leads directly to discriminatory outcomes in real-world applications. We mentioned documented disparities where systems are less accurate for certain skin tones or genders. When these bias systems are used to inform decisions in critical areas like hiring, loan applications, insurance pricing, healthcare diagnostics, or even criminal justice risk assessments, they can actively contribute to and perpetuate systemic inequalities against marginalized groups, denying opportunities or assigning negative labels unfairly. As noted earlier, vulnerable populations like neurodiverse individuals, the elderly, or children are often disproportionately affected. Their emotional expressions may not align with the norms captured in the training data, leading to higher rates of misinterpretation and a greater risk of receiving biased or inappropriate algorithmic responses or decisions, which can have significant negative consequences for their well-being, access to services, or social inclusion. Two foundational ethical principles facing significant challenges in effective computing, according to our sources, are consent and transparency. Obtaining truly informed and meaningful consent from individuals when dealing with this technology is incredibly difficult. The technology is complex, the data collection and analysis practices can be opaque, and the potential uses and misuses are not always apparent upfront, even to the deployers sometimes. Users often agree to lengthy, unreadable terms of service without fully understanding what types of emotional data are being collected, how it's being analyzed, how accurately or inaccurately it's being interpreted by the AI, or for what specific purposes it might be used now or repurposed in the future.
Yeah, nobody reads those terms.
Exactly. The subtlety of how AI might influence behavior based on detected emotion and the passive nature of data collection in many scenarios, a camera in a public place, a microphone in a smart device listening in the background, further complicate obtaining truly active, specific, and ongoing consent.
And if the AI is a black box, even if you somehow did give truly informed consent, you still don't really know how it's making decisions about your emotional state, right?
Exactly. The black box nature of many advanced AI models means that even if you consent to your emotion being analyzed, you often have no way of understanding how or why the AI reached a specific emotional assessment about you. This opaqueness erodes trust and makes it extremely difficult, if not impossible, to contest or seek redress for potential errors or biases in the AI's interpretation, particularly in sensitive applications where the stakes are high. Individuals should ideally have a right to know when their emotions are being analyzed, how those assessments are being used, and have meaningful control over the collection, use, and dissemination of this deeply personal data. This also ties back into the fragility of consent we discussed earlier. If the AI can subtly influence you based on your detected mood, are you truly making autonomous choices anymore? And does consenting to use a service today mean consenting to having your fleeting emotional states captured, stored indefinitely, and potentially reanalyzed for completely different purposes years down the line? The loss of ephemerality fundamentally changes the nature of what is being collected and how consent should be approached. It's not just about the present moment anymore.
This brings us to accountability and responsibility. When an AI system designed to interpret emotion makes an error that causes harm, perhaps contributing to a misdiagnosis in healthcare, an unfair hiring decision rejecting a qualified candidate, or maybe even an accident if it's used in a driver monitoring system that fails, who is to blame? The developers who wrote the code, the company that deployed the system, the user who relied on it, the AI itself.
That's a critical question, and our sources point out that there is currently a significant lack of clear legal and regulatory frameworks that define responsibility and liability when AI systems, particularly complex and opaque ones like Motion AI, cause harm. This accountability vacuum makes it difficult to ensure that systems are developed and deployed responsibly with adequate testing for safety and fairness, and it can leave individuals who are harmed without effective recourse. Establishing clear guidelines, standards for safety, accuracy, especially across diverse groups, and ethical use along with mechanisms for oversight and redress is crucial but challenging to implement effectively, especially given the global nature of AI development and deployment.
Finally, beyond these specific harms, there are broader philosophical concerns mentioned in the sources about human dignity and what some might call the inherent unnaturalness of AI, encroaching on the deeply human domain of emotion.
Yes, some of the debate touches on the idea that building AI that attempts to understand or simulate emotion could somehow diminish what it means to be human, perhaps making human emotions seem like something that can be easily quantified, predicted, controlled, or replicated by a machine, stripping them of their depth and mystery. There's also a related concern about the risk of over-reliance on AI for emotional validation, companionship, or support. While AI companions might offer comfort or reduce loneliness for some, an over-reliance could potentially devalue authentic human-to-human relationships, lead to emotional dependency on non-sentient systems, and perhaps even impact our own human capacity for emotional self-regulation, resilience, and understanding if we outsource emotional processing to machines. Our sources also caution against the phenomenon of ethics washing, where organizations publicly claim adherence to ethical principles regarding AI, establishing ethics boards or publishing guidelines, without genuinely implementing those principles in their actual development processes or business practices.
Right, looking good versus doing good.
Exactly. This can create a false sense of security, potentially deflect from the need for meaningful external regulation or oversight, and ultimately undermine public trust in the field if the ethical commitments are perceived as superficial or merely performative. Many of these ethical issues, from bias to surveillance to manipulation, arguably stem from a fundamental misalignment. The rapid development of powerful technology, often driven by technical capability or commercial incentives, with ethical considerations lagging significantly behind or being treated as an afterthought. The dual-use problem is also highly relevant here. A technology developed with benign intentions, like improving human-computer interaction for accessibility, can be easily repurposed for ethically questionable applications, like mass surveillance or political manipulation. Market demand and the pursuit of profit can easily overshadow concerns about accuracy, fairness, potential for misuse, or long-term societal impact.
And consent becomes incredibly fragile, as you said, if you can be subtly influenced based on your mood, or if fleeting expressions become permanent data points without your explicit ongoing control.
Absolutely. Does agreeing to use a social media platform imply consent to have your emotional reactions to content analyzed in minute detail and used to tailor what you see or how you are targeted by advertisers or political campaigns in ways designed to maximize engagement or influence, even if it exploits negative emotions? The loss of ephemerality fundamentally changes the nature of what is being collected and how consent should be approached. Transient states become permanent data, potentially creating a detailed emotional profile over time. Ultimately, the broader ethical debate is about the kind of future we want to build regarding human-AI relationships. Will AI primarily serve as a tool to augment human capabilities, a companion offering support, a guardian ensuring safety, or potentially a controller or manipulator shaping our behavior? Each of these roles carries vastly different ethical landscapes and power dynamics. While Picard's early vision leaned towards enabling more natural, perhaps supportive, interaction, the current applications and potential misuses raise serious questions about AI potentially diminishing human skills, autonomy, or connection, if not guided by strong ethical principles and public values.
It is indeed a complex moral compass to navigate. These ethical debates feel just as significant, if not perhaps more so in the long run, than the purely technical challenges of building the AI itself.
I would agree. They are intrinsically linked. Biased data leads to unfair outcomes. Lack of transparency hinders accountability, and addressing them thoughtfully, proactively, and with input from diverse perspectives is absolutely essential as these technologies continue to advance and become more deeply integrated into our lives.
Okay, we have covered a tremendous amount of ground today in this deep dive. We've charted the evolution of AI's fascinating and often challenging quest to understand human emotion, starting from those early, simple conversational programs like ELIZA that revealed so much about us, moving through the physical social robots like Kismet, to today's sophisticated multimodal deep learning systems. We've explored the diverse and complex techniques being used to decode potential emotional signals from faces, voices, physiological responses, and text. And we've delved into the significant conceptual, technical, and ethical challenges that make this pursuit so difficult, prone to error, and fraught with profound implications for individuals and society.
That's right. We've seen incredible, rapid technological advancement, particularly in the last decade, fueled by deep learning and the availability of data. But we've also seen the persistence of fundamental hurdles stemming from the subjective and ambiguous nature of emotion itself, the inherent limitations and biases in the data used to train these systems, the technical difficulties of capturing and interpreting context and individual variability, and crucial issues around transparency, privacy, manipulation, and accountability. These technical and conceptual difficulties are deeply intertwined with the profound ethical questions surrounding potential bias and discrimination, the erosion of privacy through surveillance, the risks of emotional manipulation, challenges in obtaining meaningful consent, and broader concerns about human dignity and the future of human interaction.
And threading through all this, from ELIZA right up to today's most advanced MLLMs, is that central lingering question you raised right at the start. What does it truly mean for an AI to understand human emotion? Has our deep dive shed any more light on that?
It's the understanding conundrum, and it's perhaps the most important takeaway, though maybe not a satisfyingly simple answer. Current AI systems, as our sources describe them, are excellent at sophisticated pattern recognition, correlation, and classification. They can learn to associate complex patterns in data, a configuration of facial muscles, a specific acoustic profile in the voice, certain word choices in text, a pattern of physiological change with the emotional labels they were trained on by humans. While this pattern matching can be impressively accurate in specific constrained scenarios, like recognizing posed expressions in clean data, it doesn't necessarily equate to a human-like comprehension of the subjective experience of that emotion, its rich meaning, its personal significance to the individual feeling it, or its deep connection to cognition, consciousness, and lived experience. There remains a substantial, perhaps fundamental, gap between recognizing statistical correlations in observable data and genuinely grasping the lived reality of a feeling. So if AI's understanding remains primarily pattern matching and classification, maybe incredibly complex pattern matching, but still pattern matching, then applications built on that capability risk being superficial, potentially misleading, and even harmful, especially if we project human-like empathy or comprehension onto them, falling for the ELIZA effect all over again.
Exactly. True empathy, that capacity to understand and share the feelings of another, which is often an aspirational goal mentioned for human-AI interaction, like in healthcare or companionship roles, arguably requires much more than just accurate classification of external signals. It likely needs an ability to appreciate the internal state, the perspective, the history, the values, and the context of another being in a way that is currently far beyond the capabilities of even the most advanced AI systems we have today or foresee in the near future. Assuming AI feels or understands like we do based on its responses is a significant leap and potentially a dangerous one depending on the application. This brings us squarely back to that duality of potential we discussed at the beginning, the immense promise versus the significant peril.
On the one hand, the potential for using these technologies to augment human capabilities and contribute positively to human well-being is undeniably vast. Emotionally aware AI, if developed and deployed carefully and guided by strong ethical principles, could potentially transform access to mental health care screening and diagnosis, offer truly personalized and adaptive educational experiences that respond to student needs, enable more intuitive and helpful human-computer interaction for everyone, including those with disabilities, improve customer service by better understanding needs and frustrations, and enhance safety in critical domains like automotive travel by detecting impairment. These are genuinely transformative possibilities for good. On the other hand, the risks are equally significant and demand our utmost vigilance if development and deployment proceed without careful consideration, ethical constraints, and robust governance. The potential for amplifying societal biases could lead to widespread discrimination in critical areas of life, further disadvantaging marginalized groups. The collection and analysis of intimate emotional data risks, eroding fundamental privacy and enabling pervasive surveillance by corporations or states, chilling dissent and authentic expression. The power to recognize and potentially influence emotions carries the inherent risk of widespread, subtle, and potentially covert manipulation for commercial, political, or social gains. And as we discussed, an uncritical over-reliance on AI for emotional connection or validation could potentially devalue authentic human relationships and impact our own emotional capacities and resilience.
It sounds like successfully navigating this future, reaping the benefits while mitigating the harms, isn't just about building technically better algorithms or more powerful systems.
It absolutely isn't. Our sources strongly emphasize the imperative for deep, ongoing, interdisciplinary collaboration. The challenges and opportunities presented by effective AI are too complex, too multifaceted, too intertwined with what it means to be human for any single field, whether computer science, psychology, or ethics, to address alone. Meaningful progress, both technically in building more nuanced and reliable systems and ethically in ensuring they serve human values and rights, requires robust, sustained collaboration between AI experts, psychologists, neuroscientists, sociologists, anthropologists, ethicists, legal scholars, policymakers, educators, and, crucially, the public itself through open dialogue and participation. This collaborative approach is vital not just for creating more accurate and robust AI models that account for human complexity and diversity, but equally and perhaps more importantly, for co-creating the ethical frameworks, technical standards, safety guidelines, and governance structures needed to guide responsible development and deployment and prevent foreseeable misuse.
Looking ahead then, what are some key future research directions and needs in this space, both technically and ethically?
Technically, future research really needs to focus on improving accuracy, robustness, and fairness, particularly in recognizing spontaneous, real-world expressions across diverse populations and cultural contexts, moving beyond the lab and homogeneous datasets. There's a crucial need to move beyond classifying just a few basic categories toward recognizing the full spectrum of fine-grained, complex, and mixed emotions that actually characterize human experience. Enhancing AI's ability to understand and integrate the crucial roles of situational, social, and temporal context is paramount for moving beyond superficial classification towards something resembling interpretation. Creating larger, more diverse, representative, and ethically sourced data sets is absolutely critical, and this requires developing transparent and reliable annotation protocols that explicitly account for subjectivity, potential biases, and cultural variation. And continued advancement in explainable AI, XAI techniques specifically tailored for complex emotion recognition models is essential for building trust, diagnosing errors, ensuring fairness, and enabling meaningful accountability, especially in sensitive applications.
And ethically and societally, what's needed to guide this powerful technology?
On the ethical and societal front, there is an urgent need for clear ethical guidelines, enforceable industry best practices, and potentially formal technical standards that prioritize human well-being, privacy, autonomy, and fairness above purely commercial or technical goals. Thoughtful exploration of effective regulatory approaches is required, finding the right balance to mitigate the significant risks like bias, surveillance, and manipulation while still fostering responsible innovation that genuinely serves the public good. This is a difficult balancing act. and critically promoting broad public awareness, digital literacy, and critical thinking skills about how these emotion AI systems work, their inherent limitations and potential biases, and their potential impacts is absolutely essential for empowering individuals to understand when and how their emotional data might be being analyzed, to make informed choices, and to participate meaningfully in shaping the future of this technology through democratic processes. The idea of a human in the loop is often discussed for ethical AI in general, and it feels particularly complex, yet potentially crucial for emotion AI specifically. Given the inherent subjectivity of emotion, the current technical limitations in accuracy and context understanding, and the significant risks of bias and misinterpretation, maintaining meaningful human judgment, oversight, and the ability to intervene or override the AI seems indispensable, especially in high-stakes or sensitive applications like healthcare, employment, or education. But effectively and equitably integrating human oversight into real-time systems or implementing it at scale presents its own significant practical and procedural challenges. How do you do that meaningfully without creating new bottlenecks or biases?
So where does this leave us? After this extensive deep dive into the evolution, techniques, challenges, and ethics of AI and human emotion, what's the ultimate takeaway for you, the listener?
Well, here's where it gets really interesting and perhaps offers a slightly different perspective. Our sources suggest a final, quite provocative thought that connects this whole technological pursuit back to ourselves in an unexpected way. Could the very act of trying to build AI systems to understand human emotions, grappling with all these challenges we've discussed, paradoxically, lead us humans to a deeper, more nuanced understanding of human emotions ourselves?
Wait, so you mean in the process of trying to teach machines what emotion is, we actually end up learning more about what emotion is for humans? The struggle itself teaches us.
Exactly that. As Rosalind Picard suggested in the early days, affective computing can serve as a kind of crucible, a demanding testbed for refining and validating scientific theories of emotion, cognition, and social interaction. The technical challenges we encounter when trying to computationally model affect, for instance, discovering that existing psychological frameworks might not fully capture the variability or context dependence of emotions when we try to apply them rigorously to diverse real-world data, force us to critically re-examine and potentially refine those foundational concepts in psychology, neuroscience, and even philosophy. The pressing technical need for better, more representative data that drives new, more rigorous, and diverse data collection efforts, which in turn sheds new light on how emotions are actually expressed and experienced across different cultures, demographics, ages, and contexts in ways we might not have systematically observed or understood before. This iterative process, where the challenges, failures, and insights gained from developing AI feedback into and enrich the human sciences and vice versa, could become a powerful engine for discovery. It could deepen our understanding of both artificial intelligence and, perhaps more profoundly, human intelligence and the nature of our own affective lives. The pursuit itself might be as valuable for the insights it gives us about ourselves as for the specific technological artifacts it creates.
That's a fascinating and actually, quote, hopeful thought to end on amidst all the complex challenges and serious ethical concerns. It suggests the future isn't just about the technology's capabilities, good or bad, but also about how this entire pursuit might change our scientific and even personal understanding of what makes us human and how we choose to integrate this evolving capability into our lives and society.
Precisely. The path forward demands far more than just technical ingenuity and faster computers. It calls for profound ethical reflection, a steadfast commitment to human-centric design that prioritizes well-being, dignity, fairness, and autonomy, and a genuine willingness to engage in continuous, open, and inclusive dialogue across disciplines and with the public about the kind of effective future we collectively wish to create.
The ultimate goal, it seems, should be AI that genuinely augments human capabilities, that enhances well-being, fosters understanding, and respects the richness and complexity of human experience, not systems that seek to control, manipulate, or diminish what it means to feel. Guiding this evolution thoughtfully, responsibly, and ethically is the crucial task ahead, ensuring that the algorithmic art, if it is ever to beat in any meaningful way, does so in harmony with fundamental human values.
A worthy goal indeed, and one that requires our ongoing attention, scrutiny, and collective wisdom.
Thank you for joining us on this deep dive into AI's quest to understand human emotions. We hope you feel a little more informed, perhaps a little less overwhelmed, and maybe even a little more curious about this incredible, complex, and rapidly evolving area right at the intersection of technology and what it truly means to be human. Subscribe to the channel Silent Mind Studio and follow us to keep diving into topics like this. Until next time.